Okay, so real numbers. You've been working with real numbers ever since you started working with numbers a long time ago. We use an R to note a quick way to note real numbers. And for rational, the letter is a Q. Rational numbers and irrational numbers are both real numbers. The letter we use for irrational is an I. Now the reason we used a Q for rational is because we already used an R for real and we can't have two that are the same. Alright, rational numbers. I filled in the definition for you. Numbers that can be written as fractions with integers on the top and the bottom. Okay, so anything that is a fraction is rational. Also, any decimal that is repeating or terminating. Okay, so do we all have an idea of what the word repeating means? It means something is going to happen again over and over, right? You're going to see a pattern. What about the word terminating? What does that mean? What if something terminates, it what? Disappears. Okay, disappears. What might be a better word for that? It stops. Okay, so it's a decimal that's going to stop. It's not going to keep going. But yes, disappear and stop, kind of, I could see how those are related. All right, we're going to talk about some examples now. So I said anything that can be written as a fraction, also a repeating or terminating decimal. So we're going to write some examples of that. Here's your first one. It's a fraction, 3/4. Here's an improper fraction. It's still rational. Here's a mixed number, 1 1/3. Still a rational number. All of these are going to be rational. We're going to switch over to decimals now. That's a repeating decimal, I know, because of the bar notation. Okay? Here's a terminating decimal. Remember, terminate means stop. That decimal stops after the 1. It does not keep going. Here's another repeating decimal. This time it has 2 digits repeating, the 6 and the 1. All those decimals are rational. Now we're going to switch over to some different things, like an integer or whole number, 2. Could I write 2 as a fraction if I wanted to? What would I write? 2 over 1, right? It would be a fraction. Okay, what about a negative integer, -5? Could I make that into a fraction? I could. You can have negative fractions, like -1/2. You could have negative improper fractions, like -4/3. You could have a negative repeating decimal. This is going to be a little different than what you've seen so far because I'm not going to use bar notation. I'm using these 3 dots, which is called an ellipsis. The dots show you that the number keeps going on forever, so it doesn't stop, but do you see anything repeating? You don't see the 8 repeating? You don't see a bar, but do you see the 8 repeating? Yes, this would work. Okay. And I'm going to put one more example down here. I ran out of room. A negative terminating decimal. This one stops after the 5. Okay. Any amount of money that you would have or write out in number form would be a terminating decimal, right? Money is written in decimal format. Okay. All right, we're going to move to irrational numbers. So if rational is any fraction and any repeating and terminating decimal, the only thing that's irrational is something that's non-terminating, meaning it doesn't stop or it doesn't repeat. Okay. The main things that are irrational are when you try to take a square root of a number that is not a perfect square, because you're going to get a long decimal which does not repeat and it does not terminate or stop. So you give me an example of a perfect square. What number do you know that's a perfect square that has a square root? 25. What's the square root of 25? 5. So that means 25 is a perfect square. Now give me a number that's not a perfect square. 7. Okay, so watch what happens when I put 7 on the calculator. The square root of 7, sorry. Remember, how do I get it to change to a decimal? Hit this button right here. Okay, So the calculator stopped that decimal, but we know that's because it only allows that many digits. It really didn't stop after that 1. It would have been a non-terminating decimal. The calculator rounded it off. Okay? So the square root of 7 would be a perfect example. Let's put that down. Square root of 7. Okay, let's also do the square root of 12. Let's switch and do a negative one. The opposite of the square root of, let's say, 20. Now let's switch over to decimals. What's a decimal going to look like if it is irrational? Well, it's going to keep going, which is shown by that ellipsis, those 3 dots. And you don't see a pattern this time, do you? 1, 2 is not a pattern. That is repeating. It could be a negative decimal that doesn't stop and doesn't repeat. All right, here we are to the biggest one that I need you to remember. Like, you're going to have to know this, and you should know it after today. Pi, okay? Pi is the most common irrational number that you're going to see over and over and over again, okay? All right, so now at the bottom, we're going to talk about different subsets of rational numbers. So we broke down real into rational and irrational. Now we're going to take rational and break it down further. Okay? You've been working with these kinds of numbers for a long time. Rational numbers. Remember, rational numbers is represented with what letter? Q. So rational numbers are broken down into smaller groups. The smallest group, or the most specific group, I guess the least inclusive group you could call it, is going to be your natural numbers. Natural numbers are what's called counting numbers. You've known counting numbers ever since you first started learning numbers, probably before you ever even went to school. When we count, what number do we start with? 1, 2, 3, 4. So it starts at 1 and it goes up. So it starts at 1 and then it's the positive integers. All right, what's next is whole numbers. What is the only difference you see between what we talked about being natural numbers and now for whole numbers? What's the only difference you see in the list? It starts at 0. So whole numbers are only different than natural numbers because they include a 0, but it still starts at 0 and counts up positive integers. All right, and the last group, which is the most inclusive, is going to be your integer group. And integers are represented with the letter Z because we already used the letter I for irrational. Integers don't just include 0 and the positives. Now we're also going to include the negative integers, okay? All right, I'm going to give you a bunch of examples here at the bottom. I'm going to say them out loud, so if you can keep up just by following my voice, that's great. If you get lost, you'll have to look at the screen. -1/2, 3/7, 0.75. Now we have a negative terminating decimal, -0.1. Now we're going to have a negative repeating decimal, -1.7 with the 7 repeating, shown by bar notation. And finally a bigger terminating decimal, 19.175. Those are all rational. I'm going to keep going on the next row. Here we have a negative mixed number. That's still rational. Now I'm going to get into integers. How about -1? How about -6 and -123? 0 is rational. Positive integers are rational, like 2 and 7. Even really big numbers like 98 or 1,345. My final example of a rational number is going to be a decimal that doesn't terminate, but it is repeating. What's repeating on that decimal? The 7, okay? All right, what's the most common irrational number I just told you to memorize? Pi. So our first example of an irrational is always going to be pi. You can also have the opposite of pi, or you might say negative pi. Square roots of non-perfect squares, like the square root of 2, the square root of 5, the square root of 23. Also, they're opposites. The opposite of the square root of 2, and the opposite of the square root of 5, and the opposite of the square root of 23 would all also be irrational. My final example for irrational numbers is going to be a decimal that doesn't stop, which you can see by the ellipsis, and it does not show any repetition either.